Good evening, friends. Now, today we will solve one more problem on springs. If you remember yesterday's problem, let me go back to the yesterday's problem. In this problem, what happened was you had one spring and you had two blocks. This mass started moving with an uniform velocity. Okay, and it hit it. And as a result of it, I just suggested that one of the major concepts that you need to use here is relative velocity of the blocks connected with the spring is equal to 0. In that case, there is a maximum compression being observed. Okay, that's what we had seen. Now, instead of just moving at a uniform velocity, now in this problem, what I do is I have connected both the blocks with a spring and I have given an impulse, and that too only to one block, not both the blocks. Conditions are all remaining the same, which means what? I have just given a velocity here. Okay, I just pull the block like this, just left it. And the question is, when I pull it, what is the maximum elongation that the spring will suffer? Now, students answer it is he has ignored this block as usual. Okay, and then he said, anyway, I am given some velocity here, which means this has some kinetic energy. The spring will extend only because of the kinetic energy of this block M2. So thus he has used half M2 V naught square is equal to half K X square. Or just solving this, you get X equal to square root of K by M. Very simple way. Okay, but what is that mistake he has done? If you have seen my previous video, you would have understood by now that the basic mistake that he has committed is when you give some energy here, this energy goes in extending the spring. At the same time, it moves this object also. Why? Because there is no friction here, right? Even if you give you 1 nanometer per second, this 1 nanometer per second is also some amount of energy. This energy, okay, is equally distributed by both of them. Now, if that is the case, how can you ignore this energy, right? So this is what happens. So if you ignore this, the first thing that you need to look at here is two masses of mass connected with a spring of spring constant K. So when you say two masses, this is not being fixed. Okay, that means it can definitely move and there is no friction here. I have not written friction 0. Okay, but this is the extension of the problem. I have taken this one. So now, so if that is the case, now how do we solve this? Now, once again, we use the same old concept. When you are, just find out what is the initial velocity. Initial velocity is V0. That means let us use our conservation of momentum. Conservation of momentum. I hope you got the misconception, right? Misconception is nothing but we assume that M1 will not move when you apply an impulse. Okay, that is what a misconception here. Definitely, when you apply a velocity here or an impulse over here, you see that there's an energy being imparted to the block M2. This in turn, okay, is given an energy to the spring, and this in turn is given an energy to the mass M1 also. Okay, or if you want to answer this question, you should ask a question like, see, I have put a mass M1 and I assume that, okay, so there's a velocity V0 given over here. So as a result of it, let us say spring gets expanded by a length equal to x naught. If the mass M1 becomes 100 times M1, okay, that means a massive block, then will I get the same extension? Will I get the same extension? No. Which means this mass, the contribution of this mass to this extension should not be ignored. Okay. See, this is where, so we should ask questions, okay, in the other way around to get a proper answer. Okay. So therefore, so definitely this mass should not be ignored. Next comes, okay, how do you solve? The first thing that you should know is you should reason. Okay. So this is the way how I reason. This is the way how I look at it. Okay. So therefore, now my expression, this way of doing things is incorrect. Okay. Now we have got that mindset. So towards it, what is the initial momentum of this block? Initial momentum of this block should be M2 into V0, right? Or just a moment, my pen is giving some problem. Just give me a moment. Okay. So now, as I told you, shall we use the conservation of momentum? Just a moment. Okay. Shall we use the conservation of momentum? If I use conservation of momentum, I ask you this, what is the initial momentum of the mass M2? Now you see, Initially, before I applied an impulse, this was also 0, this was also 0. Okay, so I don't get any appropriate result behind it. So which would be quite difficult for me to approach. Now, instead of it, what we can do is, let us use, instead of COM, let us use CM. What is CM? Chief Minister? No, it is center of mass. Center of mass. Okay, I have two objects over here as of mass m1 and m2. I want to find what is the center of mass velocity of this. Okay, so why center of mass? I'll come back to it. You'll understand at the time. So center of mass velocity is given by the formula m1 v1 plus m2 v2 divided by m1 plus m2, which should now be equal to, what is v1? v1 is the velocity of the first block. What is, say, v1 is the velocity of the m1, and what is v2? v2 is the velocity of m2. Now, initially at t equal to 0, what did we see? We see that this m1 did not have any velocity. So therefore, I will just write this as m1 into 0 plus m2 into, what is the v2? v2 is going in the forward direction. It was v0. At time t equal to 0, this is what is the condition, right? Divided by m1 plus m2, which should now be equal to m2 v0 divided by m1 plus m2. This is my center of mass velocity. Why did I find that? I'll come back to it once again. Just have some patience. Okay. Now, we know from the previous example that the maximum elongation or maximum compression will happen only when, okay, let us say, after some time, this will have a velocity v2, this will have a velocity v1. Okay. Now, if this v2 minus v1, that means if both of them are having the same velocity, okay, if v2 minus v1 is equal to 0, then definitely maximum compression would be, or maximum elongation would be observed. What we do is, let me use the conservation of energy principle here. When I use the conservation of energy principle, what do I have? Or maybe I can also use work energy theorem. Easier to do work with it. Okay. So work energy theorem. Work energy theorem. Both are same. Okay, you can use either of them, but I feel let us use work energy theorem, which becomes more easy for us. It says that kinetic energy, initial kinetic energy minus final kinetic energy is equal to final potential energy minus initial potential energy. See, here if I take initial, final, here I should take the reverse, ulta. Okay, final and initial. Now towards it, what is my initial kinetic energy? See, only this block had a kinetic energy. This did not have any kinetic energy, right? Half m v naught square minus, what is final kinetic energy? What do you mean by final kinetic energy? This block started pulling and the spring started expanding. Then there, at the same time, the tension in the spring started making this block also moving, right? So as a result of it, we did not get a maximum elongation here. After some time, v1 and v2 were equal, right? Okay, which means both of them are moving with some common velocity. What is that common velocity called as? That common velocity is nothing but your, which one? The center of mass velocity. That's why we found out this center of mass velocity. Okay, so therefore, this should now be equal to half into. Now you can ask me, okay, if that is the case, which block should I consider? Final kinetic energy is because of both the blocks. So I will write this as half into m1 plus m2 into VCM. What is VCM here? Into m2 into v naught divided by m1 plus m2 the whole square into whole square. This is VCM square. Okay, I have done like this. This should be equal to, what is PF? PF is nothing but potential energy, not momentum. Okay, potential energy final. What is the potential energy final? See, initially the spring did not expand. So its potential energy, initial value is equal to 0. But finally, after this block separation has changed, okay, then definitely final potential energy is nothing but your half k x square. Okay, let us solve this. So towards it, now I can write, see, I can remove this half on all the sides. Remove this half, this half, this half. Okay, and I have an, what is this m here? M is m2 here, m2 here. Very, very carefully I have to read. Otherwise, we'll be making mistakes. Then I will write m2 v naught square. I take this common into 1 minus, what do I have here? This is m1 plus m2 here. The square goes away here. So thus I will have m2 divided by m1 plus m2 is equal to kx square, right? Did I miss anything over here? No, I did not miss anything. Or this implies, now if I take the LCM, if I take the LCM here and I find out this will be m1 plus m2 minus m2, which would be m1 m2 v0 square. You can take your paper and pen and you can solve it. So you get the correct answer. Plus m1 plus m2 is equal to kx square. Or in other words, the value of k should now be equal to m1 m2 divided by m1 plus m2 square root into v0. I hope you understood this. So definitely it is not this answer. I think I make a mistake here. This should have not been k by m2. I think the answer should have been square root of m2 by k. Okay, m2 by k and into v0. This should be your answer, which the student would have written here. Okay, so here we got a different answer here. And instead of this m2, if you look at it, I've replaced this m2 by m1, m2 by m1 plus m2. Okay, what does this tell you? Can you think of what does it tell you now? It tells you that the mass that I am considering here, because both of them are moving at the same velocity, I can either write it like this. Instead of writing m2 here, I should just say this as mcm here. Okay, if you are working with this problem, then from the center of mass frame, I can just write mcm into v0 square, because they're moving at the same velocity, should now be equal to half k square. Okay, it looks like something like this, and as a result of it, you get the same expression here. So anyway, this is the straightforward approach, okay, to arrive at it. So this method can be employed only when there is no friction here. There is no friction, and as a result of it, both of them are moving at the same velocity. I hope you understood this concept. And if you like this video, do like, share, comment, and subscribe to my channel to get more updates. Thank you.